Hi everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying indefinite integrals lecture 4. In this lecture we'll be talking about by parts and partial fractions. Okay, so let's begin our lecture with integration by parts. And if you remember from derivatives, we talked about a product rule, right? So we have a product rule for derivatives and similarly we have a product rule for integration and that is called as integration by parts. Okay, now we have this particular formula and this is expanded like this one. So let's say u is called as first function and v is called as second function. Okay. Now if we want to expand this formula in terms of 1 and 2, we'll be writing first function into integral of second minus integral of derivative of 1 into integral of second, right? Now you can see that only second function is being integrated directly. We are just taking integration of second function directly. We are not integrating first function directly. We are either differentiating it or we are just keeping it aside, right? So we are integrating second function directly. So our common sense says that that's because second function must be easy to integrate, right? If we are given two functions, first and second functions, and if this one is easy to integrate, I'll keep that as second function, right? So this ease of integration idea takes us to what is called as isolate 1. Okay. So let's introduce what is isolate 1. So this is nothing but an abbreviation for inverse trigonometry, log functions, algebraic functions, trigonometric functions, exponential functions, and one number as a function. Okay. So we are not just talking about one, we're talking about one as a constant function over here. Okay. This is called as isolate 1. Now, what do we mean by that? Why are we using that? Now, you can see that this is the decreasing order of difficulty of integration, right? So this is the most difficult to integrate and this is the easiest to integrate, right? So if we go from here to here, basically from top to bottom, we are moving from highest difficulty to lowest difficulty, right? Difficulty to what? Difficulty to integrate, right? So what we'll be using this for? So let's say we have a simple integral fx dot gx dx, right? Now we'll assess if this function is easily integrable or if this one, right? So let's say if gx is easily integrable, what we'll do, we'll take it as 2 and we'll take that as 1 and we'll be using this particular table or you can say abbreviation to decide what is function 2 and what is function 1. Okay, clear? Now let's take one example of standard questions, right? That is case 1, standard questions. Now that would be simple. Let's say we have fx dot gx dx. Now in this case, there is no trick. You just have to use isolate, assign 1 and 2 and directly integrate it using the bipart formula. You don't have to do any trick over here. There's no trick involved. Simple questions, straightforward, right? Likely to be come in PGDBA, right? And now let's take one example for the same. That is case 1, right? So we have integral x cos x dx. So let's first write down isolate over here. Okay. Now you can see that x is an algebraic function, cos x is a trigonometric function. You can see that a is coming before t. That means t is basically trigonometric functions are easier to integrate as compared to algebraic functions. So we have to assign cos x as second function and x as first function. Now, according to a formula, this integral would become first function into integral of second minus integral of derivative of 1 into integral of second. This is a formula, right? So first function is x multiplied by integral of cos x. That would be sin x minus integral of derivative of 1. That would be 1 only multiplied by integral of second. That is sin x dx. Okay. So this becomes x sin x minus this is integral sin x. What is integral sin x? This is nothing but minus cos x, right? So our answer becomes x sin x plus cos x plus c obviously. Okay. And now let's solve this example. We have integral ln x dx, right? So this can be written as 1 dot ln x dx, right? So let's write down our isolate 1 over here, right? Now we can see that 1 is the easiest to integrate according to this table, right? So that can be taken as second function and this is first function. So our formula is first function into integral of second, that is x, minus integral of derivative of 1, that would be 1 by x, into integral of second, that would be x dx. So this gets cancelled out. So what we have got, ln x dot x minus dx, that is nothing but x only. So plus c. This is our answer. Okay. So now let's talk about recurring by parts and what do we mean by that? So let's say we have I equals to integral ux vx dx. So what will happen? We'll keep on integrating this integral and eventually we'll form a minus I over here, right? So that we can take on the right hand side, left hand side, sorry, and we can use that to find out the integral value. Okay. So let's see it in action. So this, let's say, gives us fx plus integral, let's say, gx dot hx dx, right? Now this is again a function which can only be integrated with the help of byparts, right? So if you apply byparts over here, let's say you get fx plus, let's say, kx and minus I over here, right? This I is being generated once again over here, okay? So what you can do, you can take this I on the left hand side, you'll be getting 2I equals to fx plus kx. I becomes fx plus kx divided by 2. Okay, so this is what we mean by recurring byparts. And now let's solve this example. We have integral e raised power x cos x dx. Now we can see that this is a product of exponential and trigonometric functions. And we know that these kind of functions cannot be solved with the help of substitution or any other standard method. So we'll have to apply byparts over here, right? So let's write down I late. Okay. Now we can see that exponential functions are coming after trigonometric functions. What do we mean by that? It means that exponential functions are easier to integrate as compared to trigonometric functions. So we have to keep e raised power x as second function and cos x as first function, right? So this actually becomes first function into integral of second, that is e raised power x only, minus integral of derivative of 1, that would be sin x minus sin x, into integral of second, that is e raised power x dx, right? Now you can see that this is also a kind of function which can only be integrated with the help of isolate or byparts. Okay, so this actually becomes cos x e raised power x plus integral e raised power x sin x dx. Let's call it as I dash, right? Now I dash equals to integral e raised power x sin x dx. Again, this is second function and this is first function. So this becomes first function into integral of second, that is e raised power x, minus integral of derivative of 1, that would be cos x, into integral of second, that is e raised power x dx. You can see that this has been formed once again over here as well, right? This is I, this was I, right? Now what we have got over here, I equals to e raised power x cos x plus e raised power x sin x minus I. So this becomes 2I equals to e raised power x sin x plus cos x, right? So I equals to e raised power x sin x plus cos x by 2, right? This is our answer. And now let's talk about case 3, that is special types of problems. And the most important thing to understand over here is isolate is not applicable in these types of problems. Isolate is only applicable for case 1 and case 2. It's not applicable for case 3, right? Although these problems are very rare and it's highly unlikely that they will be asked in PGDBA, but we'll be studying them for just in case. Okay. So we'll be deriving the first one. You can take second as homework. Okay. So the first one is integral e raised power x fx plus f dash x dx, right? Now let's further break it down. We'll be getting e raised power x fx dx plus integral e raised power x f dash x dx. Now in the usual case, we'll always take the exponential function as second function because that is the easiest to integrate, right? We'll always be taking e raised power x as the second function. But now in this case, here's the change. We'll be taking this as first function and this as second function. Okay, so let's apply byparts over here. So what we'll be getting, first function into integral of second, that would be fx, minus integral of derivative of 1, that would be e raised power x, into integral of second, that is fx only. Okay, dx. I can see that this function and this function gets cancelled out. What we are left with, e raised power x fx. Okay. And now let's solve this example and let's try to understand how to identify if this is an example of case 3 problem or not. Okay. So we have this kind of segregation over here, x upon 1 plus x whole square multiplied by e raised power x dx. Now according to our isolate rule, you can see that e raised power x is second function because it's the easiest to integrate, and this function is obviously first function, right? Now if you apply regular byparts over here, you'll be getting first function into integral of second, that would be e raised power x, minus integral of derivative of 1 d by dx upon x upon 1 plus x whole square into integral of second dx. I can see that if you differentiate this function, it would become very complicated, right? This entire expression would become very complicated again, right? So that is the biggest trigger over here to understand that we don't have to apply regular isolate over here. We don't have to use the regular first and second functions over here, right? So that gives us an idea that we have to use case 3 types of functions over here. So let's see that. So now what do we have? We have integral e raised power x multiplied by x upon 1 plus x whole square dx. Right. Now according to the standard format of case 3, we should be having e raised power x fx plus f dash x dx. Right. So how to generate this kind of format? The only way is to split this function over here. Right. Now we have 1 plus x in the denominator. So let's do one thing. Let's add 1 and subtract 1 over here. Okay. Now this actually becomes e raised power x 1 upon 1 plus x. Basically this one and this power is getting cancelled out, minus e raised power x, or let's say minus 1 upon 1 plus x whole square dx. I can see that this function is the derivative of this function only. This function is the derivative of this function only. So what we have got? We have got e raised power x. This is fx and this is f dash x dx. So this minus is a part of derivative, right? So that's why we have written plus over here. So now we have got this kind of format. Now you can directly write answer as e raised power x into fx. That is e raised power x multiplied by 1 upon 1 plus x. This is our answer. Okay. So let's take this example as a homework because that's a similar kind of problem, right? Similar kind of problem, exactly. Okay. And now let's solve this example. We have integral sine of ln x plus cos of ln x dx. Now the first thing to notice over here is we have a composite function with the argument as ln x. Now if you remember from substitution, we talked about two key rules. So the first rule was to take these arguments as our substitution, right? So let's take ln x equals to t. That would give us x equals to e raised power t, right? Now if you differentiate this one, we'll be getting dx equals to e raised power t dt, right? Now this integral becomes sine t plus cos t multiplied by e raised power t dt. Now the problem is completely over. Why? Because we have e raised power x, we have fx, and we have f dash x, right? So this has become the format e raised power t ft plus f dash t dt. Simple. And the answer would be e raised power t ft. Ft is what? Sine t. So e raised power t sine t. I can put back the substitution over here and you'll get the answer. Okay. And now let's talk about partial fraction basics, which is the last topic of today's lecture. And before moving into partial fractions, let's solve one series. Okay. So let's say we have 1 upon 1.2 plus 1 upon 2.3 plus 1 upon 3.4. Right. Now, how do we solve this series? We solve this with the help of different series. And how do we do that? We write the first term as 1 upon 1 minus 1 upon 2. We write the second term as 1 upon 2 minus 1 upon 3. And we write the third term as 1 upon 3 minus 1 upon 4. This is a very standard problem of progressions, right? So this and this gets cancelled out. This and this gets cancelled out. What we are left with? We are left with 1 minus 1 upon 4. Simple. But why are we studying this progression series in place of partial fractions? So now let's look at this particular term over here. Okay. Now I can write this as 1 upon 1 plus 1 dot 1 plus 2. Simple, right? Now, if we replace this 1 with x, we'll be getting 1 upon x plus 1, x plus 2. Now we can write this as 1 upon x plus 1 minus 1 upon x plus 2. This is what we have done over here, right? This is nothing but 1 upon x plus 1 and 1 upon x plus 2, right? So what we have done is we have converted this product into this different series. Or we can also do with the help of summation series as well, right? We can write this as plus minus over here. Simple, same thing, nothing different. So, but in case we get a function like 1 upon x plus 1, x plus 2, x plus 3. Now we cannot use our intuition over here, right? We could use our intuition practical approach over here. But over here, we cannot do that. It's become a bigger function, right? So for this kind of function, we need a proper method to convert this into a summation or difference series, right? So that is what is partial fractions, okay? So let's take the same example once again. Let's say we have 1 upon x plus 1, x plus 2, and x plus 3, right? Now, according to partial fraction rule type 1, we can write this as a upon x plus 1, some constant basically, some constant upon x plus 2 plus some constant upon x plus 3, right? We can write this as in terms of this, okay? Now, how to find out the values of a, b, and c? Let's do that. So let's take the LCM over here. So we'll be getting a times x plus 2, x plus 3 plus b times x plus 1, x plus 3 plus c times x plus 1, x plus 2. Okay. Divided by x plus 1, x plus 2 and x plus 3. Right. Now this is same as 1 upon x plus 1, x plus 2 and x plus 3. Now if we make a comparison of this numerator and this numerator, this entire function in terms of a, b and c should be same as 1 only, right? For any value of x, they should come out to be 1 only, because we have the same denominator and we assume that this function is same as this function, right? So this entire expression in the numerator should equals to 1 for all values of x. Okay, so now what we can do, we can take x equals to, let's say, 0, -1, or let's say 4. Okay, let's say we're taking these three values over here, right? And based on these three values, we'll be getting three equations in terms of a, b and c. You can use these three equations of a, b and c to find out the value of a, b and c. Okay, now once you get the values of a, b and c, you can plug in over here and find out these integrals, right? These are very standard integrals, right? Simple. So this is the practical approach on how to solve a partial fraction question. Now if you look at this example, we have integral dx upon x plus 1, x plus 2, x plus 3. This is same as this one, right? So all you have to do, you have to put these values over here and find out the values of a, b and c. We can take this as homework. Okay, so today's lecture was till here only, and this is the end of indefinite integration. So let's meet in the next lecture for definite integration. Thanks for watching.